Welcome back, students, to our Chemistry 2620 video notes. We're going to pick up in Chapter 25 with how to make amino acids. So when I say how to make amino acids, I don't mean inside of the body because this is not biochemistry, and also I'm pretty sure you have to eat those. But when we're talking about instead outside of the body. So with chemical reactions that we have seen before, let's look at how we can make amino acids outside of the body. So first, we'll start with a carboxylic acid. So here we have a carboxylic acid and a reaction way back from Orgo 1, where when you add PBr3, you used to see that in Orgo 1 that took OHs and put a bromine there, but this is a little different because we're adding Br2 with PBr3 and we have a carboxylic acid, not just a plain old alcohol. So in this reaction, it does something a little bit different and puts that bromine at the position immediately adjacent to the carboxylic acid. Then once you have a leaving group at that position, then you can do an SN2 reaction with a little bit of ammonia, and that puts the NH2 in the place of the bromine. And so now we have our base structure for amino acids. So in this other way to make amino acids, before we get into the way that we'll use, what I want to do is recall something that is going to be helpful. So in a past chapter, what we did was we saw that we could take something like diethylmalonate, add a base, and then using that base at this position here, you end up with an enolate. And then once you have the enolate, that enolate can attack an alkyl halide, and you can get an R group attached to this middle position here. Then with heat and acid, not only will that heat and acid turn these OETs into OHs, but that heat is also going to take this part and cleave it off, and that's called a decarboxylation. And so see, that gets us a carboxylic acid with whatever R group we want attached. So what we can do is use this type of reaction to prepare an amino acid. So let's look at down here. So what is similar here is we still have something that looks like that diethylmalonate, except now we have an nitrogen group already attached here. And so we still have a proton at this position. One moment, there we go, that can be pulled off with a base. So that means that we can add an R through that SN2 reaction, and then when we add some acid and heat, our OETs turn into OHs, and that heat ends up cleaving off this position. But in addition to that, what also happens is I'm going to erase some of this really quick. There we go. Is this part right here is just a unusual looking amide, right? It's only unusual because it's not the focus of the molecule. And so this is just an unusual looking amide. And remember that during the course of adding acid, all carboxylic acid derivatives, including amides, will turn back into their plain old amine and carboxylic acid. So you're going to have a, plus carboxylic acid over here from what used to be this, but you also get the amine because you had that nitrogen group there to begin with. And so this part is going through a hydrolysis reaction as well. And so now we have a lot of stuff going on with just adding acid and heat. And notice how now we also end with a something that has that general structure of an amino acid. Now, there's a lot more, but we're going to go ahead and skip the rest of section 25.3 and start talking about the structure of peptides. So remember that when amino acids come together, if there's a handful of them, they form peptides, right? And then if we have lots and lots of amino acids coming together, then we end up calling that the polymer, and that polymer is called a protein. So when we have something that's really big, it's a protein. When we have a handful, it's a peptide. So let's look at something that's a peptide. When we look at this peptide, notice how on one side over here, you have the nitrogen group. And then over here on the other side, you have the carbon group, right? And that's the carbon of the carboxylic acid and the nitrogen of the amino group. So the word terminus might kind of sound like terminal or the end. And so when we look at the word terminus, maybe in your mind, replace it with the end. And so this is the C end, and this is the N end. Right? And this works because peptides are difunctional. They have two functional groups. They all have a carboxylic acid group. They all have an amine group. And so what ends up happening when they link together is they form that peptide bond. But even though they have that peptide bond, that's only used up one of each amino acid's functional groups. So if the carboxylic acid group got used up on the left-hand side of this peptide and the left amino acid, then you still have an N group that's left. Over here, you have a nitrogen that was your part of your peptide that's on the right-hand side, and that got used up to make the peptide bond. And so what you have left over that didn't get used was your carboxylic acid. And so this is how your peptides turn into proteins, right? They're just continue to add, one on this side, one on this side, another one here, another one here, until they make this super long chain that we call a protein, which is just a type of polymer. And so the N-terminus is just going to be the side where your nitrogen functional group is, and the C-terminus is going to be the side where your carboxylic acid functional group is. And remember, they can grow from both sides. So let's look at some individual amino acids coming together to form a peptide. So here's 3 amino acids that are coming together to form a peptide. When we look at this, we can start to consider a couple of things here that we've already talked about, but it's worth a review. When your glutamic acid with the functional group of carboxylic acid comes together with cytosine, right, these two, the H and the OH, end up being removed. And what happens is you get this bond between the carbon of the carbonyl and the nitrogen. And that bond is your peptide bonds, right? And here we go, another peptide bond, because you're getting rid of the OH and the H. So when we start looking at the terminus, here is your C-terminus. And this one looks kind of weird because glutamic acid has an interesting structure where it actually has 2 carboxylic acid groups in it. And with those 2 carboxylic acid groups being involved, right, one of them is kind of like a side group. This NH2 would be your N-terminus here. So let's look at if order matters. If we're looking at dipeptides, let's look at alanine and glycine. If alanine was the one on the left versus alanine over here being the one on the right, let's see if the order of left versus right ends up creating different molecules. So Let's start with alanine glycine. We've got an NH2. Oh, and over here, look, we have an NH2. And then connected to that is a carbon with a methyl. And oh my goodness, look at that. Carbon, but no methyl. And then we have a carbonyl. Oh, I got a carbonyl. And then I have a nitrogen, and I have a nitrogen here. And then I have a carbon with no functional groups, or I'm sorry, no substituents. Oh, and then I have a carbon with a methyl. And then I have my carboxylic acid and my carboxylic acid. So these are definitely not the same compound. It looks like they have all the same components. They're just connected differently. I feel like there's a word for that. So this idea of order mattering is definitely going to be a huge deal in biochemistry, because you need your amino acids in appropriate order in certain scenarios, which is going to be a whole class. Oh, you guys are going to have so much fun. So let's look a little bit more about some convention stuff, some things that are just always the same. So when we start looking at peptides, and this is going to become really something that you talk more about in biochemistry class, but conventionally what we do is your biochemistry friends are always going to write the N terminus on the left side and the C terminus on the right side. So notice how my C terminus is over here and my N terminus is over here. And if you think about it, it kind of makes sense, right? Because if you're a biochemist and you want to clearly communicate with other people, you need as a group to have a standard so that you aren't always kind of mentally flip-flopping. Oh, wait, this one is the same, but it's just the other way around. You can't do that. You need a standard, especially because your peptides and your proteins can be so long, right? We need to make sure that there is a standard. And you're also probably going to notice that a lot of the times people start trying to make this easier on themselves, because what's going to happen is when you get into biochemistry, or maybe more biology instead of the biochemistry, I think a lot of people are going to just abbreviate the order with these 3 letters. Like, I'm not even completely sure if you have seen the structures of these kind of written out in a big chain. If you've only taken biology, that is. Because I think that biologists are caring maybe more about the order and the discrepancies in order and how that can affect bodily systems, whereas the chemists are the ones that are more concerned about the structure overall. And so in biology class, you might have seen mostly this kind of abbreviation, these 3-letter abbreviations. Whereas, as we said, chemists care about structure. Let's talk a little bit about structure. So when we talk about structure, you have started to see already in biology classes that your proteins have specific structures, right? They have that primary structure, they have the secondary structure, and so on. And so let's talk a little bit about the way a molecule behaves and maybe interlace that with some of that primary structure or secondary structure. So when we talk about an individual amide compound, we can draw resonance structures for this. And so here are our set of resonance structures for your amide group. And notice this last one here. This last resonance structure is actually one that contributes rather significantly to the resonance hybrid. Now, that's important to be told because notice how in this resonance structure, you have a pi bond between the nitrogen and the carbon that is that alpha carbon. And so that matters because in this resonance structure, what this is telling you is this carbon here is sp2 hybridized and trigonal planar. So every single one of these resonance structures illustrates the, oh, for heaven's sakes, the sp2 nature of this carbon and trigonal planar. Spelled that wrong. Let's try that again. So the question becomes, why does that matter? And it's not so much that that carbon is the one that's mattering. What matters is because this is a significant contributor, this nitrogen that you would normally say is sp3 hybridized really has some sp2 character. And so this nitrogen has a pi bond in this resonance structure. And you know that pi bonds struggle to rotate, right? So there's a barrier to rotation here. In this structure, resonance structure, where you see that single bond between the carbon and nitrogen, and here you see the single bond between carbon and nitrogen, and here you see the double bond between carbon and nitrogen. What this means is that there's enough double bond character between the carbon and nitrogen that there's a barrier to rotation. So let's look at kind of that S-cis, S-trans thing that we've talked about in the past and how that's going to relate to here. So when we look at your amino acids, what we're now saying is it might seem like this bond can just rotate quite easily, but really it takes 80 kilojoules per mole in order to rotate that bond, which is a significant barrier to rotation, meaning that that bond is pretty much set where it is. And the S-trans configuration, which would be this, is going to be the more stable one. So that's where it's going to spend the majority of its time. Whereas the S-cis is a little less stable and it's not going to spend the majority of its time there. So let's just really quick remind ourselves of what S-cis and S-trans looked like before. So we saw S-trans like this and S-cis like this when we were doing the diene chapter. I think it was chapter 16, I think. And so when you see S-trans, right, it had this general structure. S-cis had this structure. So now what we're doing is we're kind of looking at those R groups and saying these are kind of like the pi bonds that we saw up here. And notice how the bond right here is the one that has the barrier to rotation, right? That would be like this bond here and here. So why does this matter? This matters because when we have a polypeptide, which is a protein, it's not going to be completely planar, because what's going to happen is you're going to have some bonds that have restricted rotation, and that's going to be these bonds here. And having these bonds have restricted rotation is going to result in the R groups being kind of on opposite sides here, right? So that we have that S trans in general, and that we're going to see that this helps give rise to some of the things like the backbone of those beta pleated sheets. So let's talk about some other things that are going to be involved in your secondary structures. So first is, well, I guess this is the last one, disulfide bridges. So if you have seen disulfide bridges before, they are sulfur-sulfur bonds that are occurring between two amino acids. And so cytosine has that thiol functional group that is required to make disulfide bridges. So you have an SH and an SH that through a process of oxidation can end up creating a bridge between the two cytosine groups. And when you look at the bigger picture, if you're considering maybe one amino acid, and I'm sorry, not one amino acid, one protein, a cytosine and a cytosine can be linked by a disulfide bridge within one strand. Or you can have a cytosine to cytosine disulfide bridge between two different, right? These are two different strands. And so those types of things are going to also lead to some tertiary structure. So let's look at protein structure a little bit more thoroughly. When I say more thoroughly, you're probably going to open up a book and look at the pictures associated with these because I think that'll be most helpful. I also think that you have seen this in biology class and that you kind of maybe have these words memorized, but maybe looking at a picture will help take this information in your bio knowledge and just bring them together. So you should already know from biology experience that your primary structure is the sequence of your amino acids, and that these are held together, these amino acids are held together by covalent bonds. Secondary structure are going to be things like an alpha helix or a beta pleated sheet. And these are going to occur because of hydrogen bonding between those peptide groups. When we talk about tertiary structure, things like those alpha helices and the beta plated sheets are going to fold and start to get a little wild. These are going to be your globules, and your folded proteins are going to be locked into place with things like those disulfide bridges, or, of course, hydrogen bonds. Your quaternary structure is going to be those aggregates that you see in those wild pictures where they just show all of the things just hanging out together. It's pretty wild. Look in your textbook for a picture of that. So let's look at some protein functions. You know what? I'm going to let you go ahead and read these to yourself because it's been a long video than I wanted it to be, and I think you already know maybe the structure of proteins. As always, thank you for your attention. This is Katoni signing out.